Today topic is analytical block diagram of digital control system. In yesterday class, we will see the block diagram of digital control system and its limitations, advantages and disadvantages, some of the control blocks in block diagram. We can see that one. Now I am going to the analytical block diagram. That is, this is your block diagram of the digital control system, where here we are having the, already I explained last class, we are having the computer as a digital controller and digital to analog converter system with the feedback of measuring system and ADC and analog to digital controller. It is given to the feedback to the computer. Now here we are going to taking the system representation of this transfer function. That is, the system transfer function is I am taking here G of S. It is I am taking G of S. The system transfer function. This is G of S. Where measuring system transfer function is I am taking the H of S. Is I am taking the H of S. Generally, this H of S is 1. That is, we are using it as a unity feedback system. Unity feedback system. And the last one is computer controller. We are using here digital controller, no? So the digital controller is represented by the pulse transfer function. So it is the pulse transfer function, PTF. For this one, I am taking GC of S. For this one, transfer function, this total transfer function, I am taking the GC of S. So this is the blocks and these are transfer functions are I am representing like this. First one is for system, general system, the transfer function is G of S. For measuring system, the transfer function is H of S. Generally, we are using this is the feedback system and the unity of this one is unity system. Now, the third one is the digital controller. Here, I am using the digital controller. This digital controller transfer function is represented as GC of S. GC of S. So, this is the schematic block diagram of the digital controller. In this one, we are having the three major parts: computer and the computer programming, that is algorithms of the computers, and ADC and DAC. So, coming for here, the analytical block diagram, it will be giving the description of the connection, that is reference input. Reference input and compared to the feedback signal, that is with the signal sensor, and it will give the detector, error detector. The error signal can be proceeded by the controller, generate the control signal. Control signal. The control signal is can be applied to the actuator, which affects the plant. Now the output plant measured by the sensor and the compared with the reference input. The loop continue will be controller adjust the control signals based on the error input signal. This is your representation. Now I am taking here the sum of the references values, that is in blocked on blocks reference input. The reference input will be analog, it will be digital signal. Okay, why you are using here digital computer. Next one is sensor. Sensor is going to be at the feedback side section and it will be measure the output of the system. Okay, error detector. Error detector is going to be compare the input and error detector will be is going to be compare the input and ADC output. Okay, ADC output, that is nothing but input will be digital, ADC output will be digital. So the digital values will be going to be compared with the error detector. This error detector will be give the values to the digital computer values. Okay. Next, controller. Controller will be going to be control the signals, error signals. How much values we are going to be required for generating the output value. That is that one is a controller. That is, the controller will be going to be taking the algorithms in case of the digital control system. And plant, it is a plant can be represented with the dynamic elements, that is any electrical mechanical systems elements will be containing. And actuator signal will be take the action of the plant. And last one is the output. Here we are getting the desired output. So in your digital control system block diagram, the first three in linear, where compared to linear control system and digital control system, this block is same. System, measurement system, all these are blocks are same. Where we are these blocks are same. So where the digital part, this part is different. So we are going to change. We have to see what is the DAC, ADC of the systems of the blocks. Which blocks are there? ADC block, ADC and DCA block configurations and operations. So now I am going to move in the equivalent of analog to digital converter. Equivalent of analog to digital converter. So where in this block diagram, this part is a system and measurement system is a linear. Okay, system and measurement system is a linear, but where is it is a non-linear. It is a non-linear. That's why. So we have to convert that one into linear formation and given to the system input parameters. So coming for the analog to digital signal conversion. Okay. So the digital signal is a signal that represents the data sequence of decreased values at any given time. It can be taken a finite number of values. Already we know. And analog signal is a continuous signal for which the time varying the signal representation will be some time. Okay, that is analogous to another time varying the signal. This is the analog signal. So that is nothing but if you take any simple sine wave, it is the analog signal. So I want to go into this analog signal into digital form. I want to go into convert this analog signal into digital form. How it is we are going to see. Coming to block diagram. Here for analog to digital converter, we are taking the analog is the input signal. This is analog is the input signal, and we are getting the digital is the output signal. That is in zeros, ones, binary forms. We are getting the output this one. Okay, so this total ADC converter is having the blocks as sampler, quantizer, and encoder. Sampler, quantizer, and encoder. These are the blocks we are having the here in ADC converter. So coming for here these operations. First of all, see this one, sampler. So here I am taking the signal is analog signal. I am taking the analog signal. This analog signal is going to be input to the sampler. So what is this one sampler output? Sampler will be like this. That sinusoidal waveform is going to be like this. Sampler nothing but like this. If I am taking here like this, no? So reducing and again like this. So if you add this one, it is coming to as sinusoidal waveform like this. So that is sampler. It will be incoming message is going to be converted into samples. Okay, converted into some samples like this. Okay. So for example, see this one here. I am taking here sinusoidal waveform. Here, sinusoidal waveform. In this one, these are the lines or sampling lines. So the sampler will be give the output like this. When comparing these two, so I am in above figure. See sinusoidal waveform. This is a sampler. So when comparing these two, this is our output. That is nothing but sampler output will be just like a like this, lines representation. Increasing, decreasing, again started increasing, higher value decreasing, like this. So it is coming to as sinusoidal waveform. Sinusoidal waveform. After that one, quantizer. What is the main characteristics of the quantizer? We will see. For example, see about diagram representation. Here, this one. This is the quantizer. Here, for example, if you take this one is, if you take like this, okay, wait, I am taking like this. For example, if you see this one, this is a sampler now. It is a sampler for positive waveform. It is 0. Next one I am starting. Like this. This is sampler. Quantizer means it will going to be assume the voltage levels. That is, if you take this is fixed to 0. Next one is this is fixed to here 0. And next one is it is fixed to this value. It is fixed to this value. Okay, like this. See the above diagram representation like this. So this is like this representation, and it is fixed to this one, this one, this one. Again similarly for these values. Here, 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 here. Okay, and this one. So this is your quantizer. That is, the sample signals is converted into voltage levels. It is going to be fixed voltage levels. For example, if you take this is 3 volts, 4 volts, 5 volts, 6 volts, like this. It is again, sorry, it is 5 volts. It is 4 volts, 3 volts, 2 volts, 1 volt, like this. So it is time section, it is voltage level. Okay, that is we are taking the input amplifier, analog signal, sine wave, that one into convert into samplers, that is lines. Okay, some lines. After that one, that lines will be converted into as a fixed voltage levels, 3, 4, 5, 6, like this, fixed voltage levels to the from the quantizer. After that one, this 3 volts, 4 volts, 5 volts, are going to be converted into binary form through the encoder. How it is possible? Here, for example, if I am taking 5 volts is coming from here quantizer. For example, if applied voltage of this side analog signal is 5 volts. Okay, it is 5 volts. Okay, it is 5 volts. Here 3 volts is one digital component, and 4 volts and 5 volts, like this. 3 volts, 4 volts, 5 volts. Sampler to quantizer. Sampler is going to be giving the output of in the form of sampler waves. That is hold waves. Sampler and hold waves. And that sampler is going to be input to the quantizer. That quantizer will be give the output as a fixed voltage levels. So it is 3 volts, 4 volts, 5 volts is coming. So 4 volts, 3 volts, 2 volts, 1 volt, like this. After that one, this is going to the encoder. Encoder will be give the output in the form of digital formation. So what is the 8 volts of digital formation of encoder? If you know, that is 8421. This is the formation of shortcut for the encoder. 8421. Okay, I want to convert this one into 5 volts into digital formation 8421. So what is this one? Here I am representing here 5 volts. So how it is representing 8421 is the code shortcut one. So 4 plus 1 is 5 now. So 4 is plus 1 and 1 is the 1. Remaining are zeros, like this. Okay, this is the conversion of the numbers into the binary forms. 8421 is the one of the shortcut method. For 4 volts, only 4 is positive, no? Only 4 is high. High is nothing but 1. So 4 is high. So 4 is high. 0, 1, 0, 0. Okay. Next 3 volts. 3 volts nothing but what? 2 plus 1. 2 plus 1. 2 plus 1 nothing but what? 8 position is 0, 4 position 0, 2 position 1 and 1 position 1. Okay. 2 volts. That is nothing but only 2 number. So 8 position is 0, 4 position is 0, 1 position 1 high value, 1 position is 0. Next 1 volt. That is nothing but 8 position 0, 4 position 0, 2 position 0, 1 position is 1 high value. This is the conversion of integer values to binary form. Integer values to binary form. So in this way we are going to converting to analog signal into digital conversion. Analog signal into digital conversion. So first of all, here we are taking the analog signal is sine wave form. I am taking the input is sine wave form. That analog signal is going to be transferred into sampler. The sampler will give the sampling signals. After that one, the sampling signal is going to be into the quantizer. The quantizer is going to be fixed to the voltage levels. That voltage levels are going to be converted into digital form by using encoder. Okay. This is the analog to digital conversion formation. See that one. This is the functions where I am representing here. Sampler. The sampler is nothing but it samples the incoming message signal using sample and hold circuit. Quantizer. The quantizer is assigning the voltage levels into the samples. Okay. Voltage levels into the samples. Encoder. Encoder will process the sample voltages from quantizer and convert it into the digital values. Okay. Next. Coming for the equivalent of analog to digital conversion. That is, if resolution of analog to digital conversion is sufficiently then high, nonlinear effects of the quantization can be neglected. In case of the, it is one of the important. Resolution of the analog digital converter is sufficiently high, then nonlinear effects of the quantization can be neglected. Encoder is a block with unity transfer function G of S. Okay, and ADC can be replaced by the sampler. Here sampler is a switch. Remember that one. Here sampler is a switch. So that is analog to digital converter. That is digital part is going to be input to the see the block diagram. ADC block is before the computer. No, ADC block is the before the computer. So digital computer. So ADC can be replaced with a sampler. Sampler is nothing but a switch. Remember, the switch is represented with the input of this one like this here. See this one here, switch. So it will be when input and feedback is coming to analog signal is coming to from feedback. No, that is added to summing point. The summing point is going to be give the error output of this one. That error is going to be forward to the sampler or hold circuit. That is nothing but analog to digital conversion part. That is the analog digital to conversion part. So this is your representation, and here I am not mentioning the encoder. Okay, encoder, right? Okay, this is your representation of the analog to digital converter. Okay. So what is the importance of the analog to digital converter? I am saying the main role of the analog to digital converter in modern technologies, development of the process into transaction of voice communication systems from outdated analog signals, processing the more advanced voice process over IP or VoP systems, and today transiently due to the contributions. And the typewriters and other computer input devices needed to be connected to a modem it was connected a mainframe or other front of the computer system to communicate with the required computer systems. It constrains the ultra high speed works from today. So modern transmission process will be modest to do process. Now the system for smaller office applications and digital provide branch exchanges or PBX was developed using analog to digital conversion processes. Okay. Next, coming for the digital to analog conversion. Digital to analog conversion. Coming for the digital to analog conversion. Coming for the digital to analog conversion. Here, in case of the digital to analog conversion, the input is digital input and the output is analog output. You are getting. Okay, digital input is I am taking here 001s. We are converting this one into analog. Okay, so this analog is going to be applied to the system. Okay, this part where computer, DAC, system, output, feedback, here ADC, input, ADC, like this. This is one. So I am going to here now DAC, digital to analog conversion. Coming for here, in case of digital to analog conversion, same as here, we are in the digital input. That digital input is going to be decoded, and that will be going to give to the whole circuit. Whole circuit nothing but sampler. That sampler is going to give the analog output. That is, as the transfunction function of the digital decoder is unity gain, so the digital converter can be replaced with whole circuit, whole device. So this is very important. When the data from one computer to another computer, some analog signals. Here I am taking is, I am going to be transferred to the data from one computer is sent to the another device, analog carrier. That is, already I am draw here block diagram now. Here it is computer, DAC and system. What I am saying here, the computer is going to be sent to the some analog carrier signals. This digital controller is, this is digital input is different. This is digital. For system we require analog. Okay, for system we require analog. So this digital form is converted into analog form. That analog form is going to be given to the system. That is, when the data from one computer is sent to another via analog carrier, you are going to be first conversion of analog signal. Okay, analog converted into analog signal. So we have to going to analyze the characteristics of the analog signals. That is, what is the amplitude of the signal, and what is the frequency of the signal, what is the phase shifting of that signal. We are going to analyze it. So first one is amplitude. For example, if you take here, I am taking the amplitude first one. I am taking the first one is amplitude. Okay. It is one. The signal is going to be given to the system now. So this one is first case. When binary data is represented by the digital form. That is, this is the form, digital form. Okay. That is, it is higher case. After that one, it is low. Again, it is going to be starting. Again, it is low. So it is nothing but it is higher case 1, it is lower case 0. Okay. That binary, this is the binary form. Where digital computer is going to be give the binary forms no output. Computer output is binary forms now. That binary forms is here. The binary forms is going to be converted into are going to be DAC. The DAC gives this analog form. So when it is 1, it is going to be high, amplitude high. When it is 0, that amplitude nothing but in this axis. In this axis, I am taking an amplitude. It is a time signal. So it is 1, nothing but high. It is low, nothing but 0. When it is high, nothing but like this. Okay. This is the in case of the amplitude. Next, coming for the frequency. Where in case of the frequency, if I am taking, it is one higher position, that is nothing but we have a more number of oscillations. When it is 0, nothing but we are having the less number of oscillations. That is nothing but the digital form is, for this one is 1 is more number, 0 is less number. That part is going to be given to the system. That is the characteristics of the analog signal. And the last one, phase shifting. Last one is phase shifting. See that one, phase shifting. That is, after every 90 seconds, 90 degrees or 180 degrees, it is going to be phase shifting. Phase shifted. That is, for example, if you take like this sine wave, okay, wait. Take more one. It is one. After this one, some angles, this part is going to be same, like the phase shifting, 90 degrees. Again, these two coming. After this one, see, it is coming to a positive form, like this. That is nothing but it is going to be phase shifting of this for phase shift is this one. So for this phase shift 1, it is 0. Okay. It is one middle part. That is, this is 1, it is 0. This is a phase shifting of the analog signal. So these are the characteristics we are going to be analyze the system input side. Why? Because the output of the digital computer is in binary form. That binary form is going to be given to the DAC, digital to analog signal. The analog signal here going to be characterized. If it is coming, amplitude is same, or frequency is same, if it is coming to as phase shift. Okay, it is very important. If the output of this one is phase shifting will be there. That is nothing but it is continuously as in the mirror after some particular cycles. So the system behavior is going to be changing. So the desired output is going to be changing. That's why where the input of the system is going to be analyze the characteristics of the analog signals, where the amplitude, frequency, phase shifting are coming there. If frequency is coming, okay, for 1, it is 1 here. The frequency cycles will be 10 cycles is there. Okay, so for 10 cycles. For 0, it will be 5. Again for 1, it is going to be 15. That is the thing, but it is going to be changing. That is, the signal is here 5 volts. Okay, sorry, first 10 volts, no, 10 volts. Next one is 5 volts. Next one is 15 volts, like this it's coming. 15 volts, like this. So we have to characterize that input of the system from the DAC. This is very important in case of the digital to analog conversion. Now I am going to taking the total analytical block diagram of the digital control system. Okay, I am going to taking the total analytical block diagram of the control system. This is your here. The upper one is the block diagram of the digital control system. In yesterday class, I have represented. That is, input is R of t with respect to time. Output is U of k. The input is R of t is given to the digital form. The output is U of k. The digital form is converted into U of t, some amplitude. Okay, U of t. Analog form. Analog form is nothing but U of t. That U of t is going to be given to the system. The system feedback is going to be, that is output of Y of t. So this one is U of t. It is analog form, and this is analog form. Okay, this is digital form. Again, this analog form is going to be converted into digital form, like this. Okay, so I am going to be schematic this one is with this one here. That is A to D digital processor, D to A. Okay, this is your signal formation like this. Here sample is coming. And I have explained that one. Okay. Before that one, I am taking the sampler. For example, it is the input side, R of T. It is error and sampler and whole circuit, error signal. Okay. It is like a switch. Sampler, whole signal. Switch. Okay. This one is going to be given to this digital processor. This part is nothing but, this switch is part is nothing but this one. This one. Okay. All of understand? This is your analytical block diagram of the digital control system. Okay. Tomorrow we will see what is the sampler circuit, what is the whole circuit in next class. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.